All right. Hello, everyone. Welcome back from Thanksgiving. Can anyone hear me?
Yep, you're good.
Good. All right. Today, I want to talk about networking and how it relates to operating systems. And a lot of this is um, geared towards the last lab, in which you'll actually build some network interface driver. Some of it's just geared toward general understanding of how the network software typically is set up in operating systems. And then we're going to talk about today's paper on LiveLock, which illustrates an interesting danger in network and stack design. So first, let me set the general scene by drawing a few network pictures. The network, of course, connects up different hosts. There's kind of two ways in which you can view the connections as occurring. One is that for nearby hosts, they're often connected to what's essentially the same network. So there may be a single Ethernet, and maybe this is a switch or a cable, and you might have a bunch of hosts connected to this Ethernet, where hosts are maybe laptops or servers, or as it will turn out, routers. The way network software is designed is to kind of try to ignore as much as possible the details of exactly what this network is that directly attaches hosts. It might be a single cable, which is probably the case at the time today's paper was written. This might be an Ethernet switch. This might be some sort of Wi-Fi, wireless LAN, and these things aren't wires at all, but rather radio links. But for the most part, these differences in sort of exactly what the local connectivity is are kind of totally papered over at a pretty low level in the networking stack. And so on each of these hosts, there may be different applications. Maybe there's a web browser here and a HTTP server over here, and they need to talk to each other across this network. Now, there's a limit to how big you can build a single local area network. So for which the abbreviation is usually LAN, local area network. And the way to think about it maybe is that a local area network can be as large as the network in which it makes sense for all the hosts to be able to see all of each other's packets. That is, sometimes hosts want to broadcast to all of the local hosts. That works fine with a dozen or 20 or 50 or maybe even 100 hosts, but you can't really easily build single networks where all the hosts can more or less directly talk to each other with more than, say, a few hundred hosts. And so to deal with that, the way the larger internet is constructed is that there's a number of these individual LANs, maybe one at MIT, maybe one at Harvard, maybe one far away at Stanford, and there's some sort of connectivity between them, which you can think of as routers. So there might be a router that's plugged into the MIT local area network and also has perhaps a longer link to the Harvard network. And in fact, there's a network of routers, which is essentially the backbone of the internet, including long distance router to router links. So there might be a longer link across the country, and maybe this router is plugged into the some local area network at Stanford. And then we have hosts. We have this sort of more elaborate task in which we want a host at MIT to be able to talk through a sequence of routers to a host at Stanford. And this is called routing. So we need to have a way for hosts at MIT to address, to name individual hosts at Stanford. And we need some way so that routers near MIT can look at a packet sent by MIT and say, oh, that's a packet for Harvard, or a packet for Stanford, or a packet that needs to go somewhere in Japan, or who knows what. So from the point of view of network protocols, this local this local communication is taken care of by Ethernet protocols, and this long distance communication is sort of layered on top of that and taken care of by IP or internet protocols that know how to route over long distances to distant hosts. Okay, so this is what a network looks like in a nutshell. I will now want to talk about the what's inside the packets that move across an Ethernet or move across the larger internet, with an eye to eventually talking about the software that in hosts that has to process, hosts and routers that has to process those packets. So let me start with the lowest level and talk about what's inside an Ethernet packet. So when two hosts that are quite nearby, attached to the same cable or same Wi-Fi network or same Ethernet, want to talk to each other, the sort of lowest level protocol, which allows two hosts on the same LAN to talk to each other, is the Ethernet protocol. And you can think of one host one, sending a frame over the Ethernet to host two, what's called an Ethernet frame, which is the Ethernet word for a packet. And it's a series of bytes that are sent over the Ethernet from one host to another. And what the Ethernet protocol does is have just enough information in it to allow the two hosts to realize who's talking to each other and cause the host to be able to recognize packets that are addressed to them. And so what an Ethernet header looks, so the way that Ethernet deals with this is that every Ethernet packet has at the beginning a header that has 3 fields, followed by some Ethernet payload. And what's in the header is 2 Ethernet addresses, we'll call them the destination address and the source address, and also the type of the packet. Each of these addresses is just a 48-bit number that uniquely identifies a particular network interface card, really. And this type field is going to indicate to the recipient host what it's supposed to do with that packet. And what that really means is what higher level protocol should examine and process the payload of that Ethernet packet. And so these are bits that go are typically said to go over the wire. These 48 plus 48 plus 16 bits of header, and then however much payload. And not really visible to the software, but there's going to be something at the beginning of the packet that's recognized at a very low level by the hardware that signifies the start of a packet. And the receiving host needs to know when the packet ends, and so there's going to be another sort of special bit pattern at the end that signifies the end of the packet. These 2 begin and end flags are never seen by the software, but the rest of this Ethernet frame is delivered by the network interface card, the NIC at H2, to the software. If you've looked at the final lab for the course, you'll see that the software we give you includes a bunch of new files, including kernel/net.h, which contains a whole bunch of definitions of packet headers for different network protocols. And so this is just text taken directly from this net.h file we give you. And it includes a description of the layout of the Ethernet header. And this software we give you actually literally uses this struct definition in order to parse incoming Ethernet packets, that is to pick apart the head to get the destination and type. And also it uses this structure to format packets. So the host is really in charge of sort of setting up and parsing this header that's used by Ethernet. Any questions about Ethernet packets?
Yeah, I had a question.
Please.
Is the bit pattern you mentioned that the hardware uses to determine the start and end of a packet similar to the EOP in the lab, which is the end of packet?
No, the EOP is a separate mechanism between the driver and the NIC to help them communicate. This is, there's some electrical scheme, there's some low-level electrical or optical signaling scheme to transmit bits over Ethernet cables. And these flags have to do with, they're typically electrical patterns that would not be legal inside a packet. And so, one scheme is to, instead of just sending 0 or 1 bits over the wire, you could send sequences of 2 signals. So there's 4 different symbols possible with sequences of 2 different, electrical voltage levels or something, and have 2 of the 4 possible symbols indicate 0 or 1 bits in the body of the packet, and have the remaining 2 indicate beginning and end. And that was in fact a scheme that was used years ago. A scheme much like that was used years ago in Ethernet. I don't actually know how it works now. Okay, something to know about these addresses is that these are 48-bit addresses. The reason for the 48 bits is that they wanted to make sure that there was enough bits to be able to give a unique address to every different NIC ever manufactured. So there's a vast number of possible addresses. The internal structure of these 48-bit addresses is that the first half, the first 24 bits, is a manufacturer number, and there's every manufacturer of network interface cards, of NICs, has its own manufacturer number. So that's the first 24 bits. And the second 24 bits is just any number, it can be any unique number assigned by the manufacturer. So manufacturers typically assign them in just ascending order. So if you buy, half a dozen network interface cards, the network interface card, each network interface card has programmed into it its own address. And if you look at the address, you'll see that the high bits are the same for these 6 cards you bought from the same manufacturer, but the low 24 bits are probably 6 sequential numbers. So these addresses are unique, but what they're not helpful in is locating the destination host. So if you know the host you're talking about is on the same local area network as you, you can use an Ethernet address, and it's on the same local area network, so it will be listening for packets with its own address. But if the host you're trying to talk to is on the other side of the country, you have to use a different scheme, and that's what IP is all about, which I'll talk about in a bit. Okay, so this is what these packets look like. You can actually look at Ethernet packets in action using the TCP Dump program, and you're encouraged to do this. You'll probably need to do this as part of the lab. And this is actually the output of TCP Dump from the lab. And what TCP Dump is telling us here, was telling us a whole bunch of things. This first part is the time at which the packet arrived. If you like, you can try this on your laptops if you install TCP Dump. And the rest of the first line is a sort of human readable interpretation of what kind of packet that is. And then these next 3 lines, or this part here, is a hex dump of the received packet. And you can see, we can actually follow along with the Ethernet header. There's these first 48 bits or 6 bytes is a broadcast address. All Fs and all Fs Ethernet address is broadcast to all the hosts on the local network. The next 48 bits is the sending host's Ethernet address, which we can't necessarily tell anything about, although the high bits, in fact, this was generated by x86 running under QEMU, so no real NIC was involved. So it's not actually a manufacturer number up here. It's just something that QEMU makes up. And then the next 16 bits, the next 2 bytes, is the type. It's the Ethernet type of the packet. In this case, it's 0806, which is a protocol called ARP, which I'll talk about in a moment. And the rest of this stuff is the payload of an ARP packet, which I'll also talk about. Any questions about what we're looking at here? This is well worth trying out on your own computer if you care about networks. Okay, so the next protocol that's of relevance to the lab and communication over an Ethernet is called ARP. So at the Ethernet level, every host has a 48-bit Ethernet address. But for communicating over the internet, it turns out you need to use a 32-bit internet address. And the reason why internet addresses are different is that internet addresses have internal structure. In a 32-bit, in a host's 32-bit internet address, the high bits are full of all kinds of hints about where in the entire internet this packet needs to go. And so you can think of an internet address as having in the high bits a network number. It's actually a little more complex than that, but it's essentially a network number. Every network in the internet has a distinct number, and routers look at the high bits in the internet address to decide which router on the internet this packet needs to be forwarded to. And then the low bits in a 32-bit Ethernet internet address, IP address, are the number of the host we want to talk to on its local network. But when a packet finally arrives when the internet packet arrives at a Ethernet, we need some way to, given a 32-bit IP address, figure out the 48-bit Ethernet address of that host. And the way the internet chooses to do that is to have a dynamic resolution protocol, a kind of request response protocol called ARP, for address resolution protocol. And the way to think about it is that when a IP packet arrives at a router, or it needs to be sent by a host to a host that's known to be on the same LAN, local area network, the sender first broadcasts on that LAN an ARP packet that's a request that says, whoever owns this IP address, please respond with your 48-bit Ethernet address. And assuming that host exists and is turned on, it'll respond with an ARP response packet. And this is the format of the packet, of an ARP packet. The way it actually shows up is inside an Ethernet packet. And so what you would actually see in the network is first the Ethernet header, which has the 48-bit source field and a 48-bit destination field. Maybe it's destination source type. So this is the Ethernet header. And then from the Ethernet point of view, the rest is payload. But actually, it's an ARP. In the Ethernet payload is an ARP packet, which has these fields, boom, 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 right after the Ethernet header. And the way the receiving host knows it's an ARP packet is by looking at this type field. And if it's 0806, that's the agreed on Ethernet protocol number for ARP. And then the receiving host software would know to hand this packet to its ARP protocol processing code. What's in these packets, and there's a bunch of junk here that basically amounts to saying, I have an internet address, I want to turn it into an Ethernet address, please respond if you own this internet address. And then these fields hold the internet and Ethernet addresses of whatever host is sending this ARP packet, and that's enough to figure out for hosts to build dynamically tables that tell them the correspondence between Ethernet and IP addresses. Again, we can use TCP dump in order to see these packets go by, and you're highly likely to see them if you run TCP dump. Here's again a TCP dump output taken from the lab, and it turns out that in the lab, your XV6 will end up talking simulated, true, but talking Ethernet protocol and sending IP packets through Ethernet, through a simulated Ethernet protocol with whatever host you're running QEMU on. And so when you run, you'll actually be able to see these ARP exchanges between XV6 and your host. And so what we're seeing here is my host knows the IP address of my XV6 and wants to figure out its Ethernet address on the LAN that QEMU simulates. And this second packet is my XV6, and you can see the code that generates this. My XV6 has seen this request, realized that it's the owner of the IP address in the request, and is sending back the response. TCP dump has nicely parsed out the fields in the ARP packet and printed them here. And I think this is the sender's IP address, and this is the this is the sender's IP address. This is the IP address that the sender is interested in. And those would presumably go in here and here. And this is the response with the Ethernet address of the owner of this IP address. And this Ethernet address would probably end up being in this field. And if we're clever enough, we can pick apart these packets and see some of these fields. As we know, this part is the Ethernet header, destination, Ethernet address, source Ethernet address, and packet type, 0806. Working backwards, this is the TIP field, which is the IP address that the sender wants to find the Ethernet address for. And if you pick this apart, there's 1 byte for each of the 4 fields of the IP address. Sorry, it's really looking for 10, 0, 2, 15. This is 10 hex, 0 hex, 2 hex, 15 hex. And then there's the target's Ethernet address, which is not known. And then the sender's IP address, 10.0.22, and the sender's Ethernet address, and a bunch of other junk here saying that we're interested in Ethernet and IP address formats. And here's this is a request, this is a response. Any questions about ARP?
Yeah, question. Why is it necessary for the sender to include its IP address if its Ethernet address is already included in the packet? Like to respond to it, wouldn't the receiver only need the Ethernet address?
Yeah, I don't know why all this stuff's in there. I think if you wanted to, you could strip this down quite a bit. You know, like the well, okay, maybe the answer is that this protocol was designed to be usable on networks other than Ethernet. And so it was designed to be fairly self-contained so that it didn't depend on anything didn't depend on anything else. And therefore, the ARP header has a copy of the Ethernet addresses. Now, in fact, if you know you're sending ARP over Ethernet, the Ethernet packet also has all the Ethernet addresses, as you can see here. So it's redundant if you're running ARP over Ethernet, but maybe if you were running ARP over something else, you'd need these fields because maybe something else packet format doesn't already include these addresses.
I see. Okay, thank you.
Yeah.
Oh, sorry. What is that part on the right where it says "RU"?
Oh, this. Okay, this is not interesting yet, but this is an ASCII interpretation of these bytes. So, well, the dot here corresponds to, you know, a byte that has no ASCII equivalent, and this, I guess, somewhere in here, 52 or 55 probably. You know, 52 is probably R, and 55 is probably U in ASCII. So this will be more interesting when we start sending packets that have actual ASCII text in them rather than binary fields.
Okay, I see. Thank you.
Yes. Okay, and I'm showing you this because you'll see these packets in the lab. Okay. Actually, there's something I wanted to there's something I want to make sure that you all caught in this discussion, and that's the habit in formatting packets of nesting protocols and nesting headers. So what we just saw was a packet that had an Ethernet header and Ethernet payload. The first part of the Ethernet payload was, you know, an ARP header. And as it happens, ARP has no remaining payload. But there are other, what we'll see in a moment is much more complicated structures in which we have an Ethernet packet that contains an IP packet. And inside the IP packet is a UDP packet. And so, you know, UDP is another protocol that you can run over IP. So there's a UDP header. It also, you know, you don't necessarily have to understand these acronyms yet, but there's a UDP header. A UDP packet also has a header and a payload. And there's times when you carry another protocol inside UDP. So for example, the domain name system has yet another format of packet defined that fits inside UDP. So what you see is that hosts that are sending packets will build up a packet. The DNS software will say, I want to send a packet over UDP. The UDP software will prepend a UDP header. We need to send that over IP. The IP software will prepend an IP header. The Ethernet software will prepend an Ethernet header and gradually build up packets in that software when it's sending. And similarly, when a system receives packets, it first gets the whole packet, and inspects the first header. It knows it's Ethernet because it received it from an Ethernet NIC. Checks some validity, strips off this header to look at the next header, and there'll be a type. This, always either a type field, or in this case, a protocol field that tells the software what to expect after the Ethernet header. So there's a type field that indicates IP versus ARP. And so the software will look at each header, validate it, strip it off, revealing the next header, check that header, interpret it, figure out what it means, strip it off, revealing the next, and sort of hand it on to the next layer of software. I'll talk a bit more about this, but this is a sort of universal way of looking at these nested packet headers. All right, so the Ethernet packet, the Ethernet header, is enough to get a packet to a host on the local area network, and if you want to send an IP packet locally, you can use ARP. But IP is used much more generally. IP is the sort of layer of the protocol that helps you deliver a packet anywhere in the internet based on IP addresses. And so this is the format of an IP packet. Again, you can find it in net.h in the source we give you. And over Ethernet, at least, the way you'd see this is in an Ethernet packet with destination, source, and type of Ethernet type equals 0800, and then the IP header, and then the IP payload. When you send a packet to a distant network, on the other side of the world, the IP header gets passed along. This Ethernet header gets stripped off after you leave the local Ethernet. Maybe a new one gets put on it for each hop that your packet is routed, but the IP header stays basically the same the whole way from the original source host, your computer, all the way to the destination host. So this header has sort of global significance, whereas the Ethernet header is really only used for each, for a single local area network. So there has to be enough information here to carry a packet all the way to the far side of the internet. And the critical fields, for our purposes, is really three very interesting fields in this packet format. The destination field, which is the 32-bit IP address of the host that we want to send the packet to, and in particular, in its high bits, it's going to have network numbers in it that'll help routers. And then when the packet's delivered, this P protocol field will tell the destination host what to do with the packet, not what to do with it next after it strips off the IP header. And if you've ever seen a MIT IP address, you'll see, well, there's a couple of different ones, but for example, if you see an internet address starting with 18, the things have actually changed in the last couple of years, but this for a long time was the network number of MIT. And so most hosts at MIT would have IP addresses whose high byte was 18. And routers all over the world would have some table where they'd look up 18 and say, aha, I know how to route this packet one step closer to MIT. So let me show you again TCP dump output. Again, actually taken from the lab that includes an IP header. Okay, so we can parse this packet. because it was sent over the Ethernet, it starts with an Ethernet header. Actually, one thing that's kind of wrong with these TCP dump, with these packets that are generated, and now that I'm seeing it, I'm not sure what the problem is. They should not start with all, these Ethernet headers shouldn't start with all Fs, because that's the broadcast address that causes a packet to go to every host. And you would not see that for a packet sent between two individual hosts, as this one is on a real network. So there's something funny going on with my solution to the network lab or with QEMU. Anyway, we have the Ethernet destination address, the Ethernet source address, and the Ethernet type. And 0800 means that the remaining bytes are IP packet. The IP packet header length, I think, is 20 bytes. Let's see if we can find the end. 215. So this must be the end of the IP header. And working backwards, because these are the fields we really care about, the destination IP field is A is 10, 10, 0, 2, 2, which is, I think, in QEMU's funny simulated network is the address of the real computer I'm running QEMU on. And then before that is the IP source address, which is 10, 0, 2, 15, which is the sender, which is QEMU's address for XV6 basically running inside QEMU. And then this stuff before it is all this other stuff. There's a 16-bit checksum, which your software is supposed to check to realize that a packet's been corrupted and should be discarded. That's this checksum. There's a 1-byte. All right, I messed something up here. Oh, this is 16. Sorry, this is 16-bit checksum. This 11 is the protocol number, which is particularly important. 11 hex is 16 plus 1, or 17. So that means that this is a UDP packet based on the protocol field. And then all this other stuff we don't really care about. It has things like the length of the packet. Any questions about IP headers? All right. Again, the critical stuff is the IP header has the IP address of the source to destination, and this protocol field is going to tell the destination host's networking stack that this packet should be processed by its UDP software, which I'll talk about right now. Okay, this IP header is enough to get a packet to any host on the internet. But we want to do better than that. Every host, is running lots and lots of different programs that need to use the network. They need to send and receive packets on the network, and so we need a way that's not in the it's not included in the IP field in order to decide which application which application on the target host this packet ought to be handed off to. And there's a couple of protocols that do that job. One of them is TCP, which is quite complex. Another is UDP. TCP is actually what's used mostly for things like the web. And TCP is a very complex protocol that not only helps your packet be delivered to the right application, but also has a lot of things like sequence numbers in order to detect lost packets and retransmit them, make sure data is delivered in order and without gaps if in case anything goes wrong. UDP is a much simpler protocol that just delivers a sort of best effort delivery of a packet to a particular application, but without any error correction or well, basically without anything else. For us, the critical fields are these 2 port numbers. And the game here is that when your application wants to send or receive packets, it uses what's called the sockets API on Unix at any rate. And this is a set of system calls whereby a process can say, look, I'm interested in packets addressed to a particular port. And it'll say, what port number it's interested, sorry, packets with a particular, I want to receive packets with a particular destination port. And the operating, so you make a system call that sets this up, and the operating system will return a file descriptor. And every time a packet arrives with the port that the application asks for, that packet will appear on the file descriptor, and the application can read it. These ports, there's really two kinds of ports. Some are well-known port numbers, like I think port 53 is the official well-known, universally agreed port number for a DNS name server. So if you want to send a request to a DNS name server, you can send it in a UDP packet addressed to dport 53. And there's a bunch of other sort of well-known ports for commonly available services with universally agreed on numbers. And then the remainder of the 16-bit port number space is used for the sort of anonymous client ends of ports. So if I want to send a packet to a DNS server, its D port will be 53, all right, but its S port will be a more or less randomly chosen number for my end, so that when that'll be associated with my application's socket, so that when the DNS server sends a reply, it'll be addressed, that the DNS server will copy the request source port into the destination port field of the reply, send it back to my machine, and my machine will use this port number to figure out which application should get the reply. Okay, so the main function here is to have these two port numbers in order to be able to hand off packets to individual applications on this machine. So feel free to ask questions. I have TCP dump output for UDP also, again, taken from the lab. So again, we have an Ethernet header and a 20-byte IP header, which probably ends here. The 11 is IP protocol 17, which is UDP. So the receiving host will know to process it with its UDP software. The next 8 bytes are the UDP header, which is shown right here. And so who knows what these port numbers are? I mean, none of this is unfortunately a packet just generated by the lab software without any special numbers in it. So these are just the port numbers that happen to choose. This must be the length of the packet. So 1B is 20 something. And this, our software for UDP and XV6 is so lame that it doesn't fill in the checksum field. But this is the header. And then after the UDP header is the payload of the UDP packet. And in this case, the application is sending ASCII text, and that ASCII text is right here. So this is a ASCII text placed inside a UDP packet, placed inside an IP packet, placed inside an Ethernet packet, and sent over simulated Ethernet.
Sorry.
Yes.
I just had a question. So when you send a package to someone, you don't know their Ethernet address. So do you just send it to your router then, and then the router figures it out from there?
If for packets sent somewhere else on the internet, let's see. Your host, if you send a packet to a particular IP address, your host software will look at the destination address to figure out if the target host is on the same local area network as you are. And if it is, it'll use ARP to translate the IP address into an Ethernet address and then send the packet over the Ethernet to the target host. So that's what happens is sort of in the special case in which the target host is on the same network. In the more general case where you're sending the packet to somewhere else on the internet, across the country, you'll send the packet to a router on the same local area network. That router will look at the destination IP address to pick the next router to decide sort of which router it's attached to, it should forward the packet to, and the packet will sort of go hop by hop through routers, getting closer and closer to the target. Does that answer your question?
Okay, I see. Yes. Thank you so much.
Someone asked if there's a limit to the length of a packet, and the answer is yes. There's a couple of different limits. Every underlying network technology, like Ethernet, but there are other things that are like Ethernet, has its own maximum packet length. So when today's paper was written, the maximum packet length was on Ethernet was 1,500 bytes. I think modern Ethernets allow packets up to around 9,000 or 10,000 bytes. But that's about the highest maximum packet size I've heard of. And the reason, there's a couple of reasons why you wouldn't want sort of infinitely long single packets. One of them is that the packets are, you're sending these packets over wires that could be quite long and subject to noise and interference. And so you do get corruption of bits when you're sending packets. Basically, every networking technology has some kind of checksum or error correcting code that goes along with every packet. But checksums and error correcting codes are only capable of reliably detecting errors over a certain number of bits, and so as you increase the number of bits, the probability of an uncaught error goes up and up. And so that limits for a reasonable size checksum, like 16 or 32 bits, that limits the maximum size of a packet. And the other limitation is that if you send huge packets, that means that all the routers and hosts involved have to have huge packet buffers to be prepared to receive huge packets. And that starts to get unwieldy and expensive because it's difficult to have variable length buffers. It's most convenient to have just a single length of buffer. And that works best if the maximum packet length isn't too enormous. Anyway, so for Ethernet, so Ethernet has a 1,500 or 9,000 byte limit. In addition, for all these IP protocols have length fields, which are 16 bits. So even if you were willing to have Ethernet have a larger packet size, IP itself has a kind of baked in maximum packet size of 64 kilobytes. Okay. Okay, good. So much for UDP. And hopefully when you finish the lab, you'll see output very much like this. In particular, the message from XV6 and a reply back from the host that you're running QEMU on. In fact, actually, at the end of the lab, you'll run software which we provide, which will actually send a DNS query to Google's DNS servers and get the response back. And our software will print the response, but your software will have done the sort of Ethernet level device driver interactions. All right, so that's the story for packet headers and protocols on the wire. Sort of corresponding to these packet formats is what's called the stack of network software that runs on the host. So if you think about what's sitting inside the host, and from now on, I'm mostly talk about sort of typical software arrangements. There's all kinds of different ways people have structured network software. And somewhat quite different from what I'm going to talk about. But I'm going to talk about kind of what I think of as at least as the sort of standard approach. So, let's assume we're running Linux or maybe XV6, and we have a bunch of applications, maybe a web browser, maybe a DNS server, who knows what, a bunch of applications. They'll have used the sockets API to open up file descriptors in the sockets layer. So there's going to be this inside the kernel, a layer of software called the sockets layer that has tables that remembers the correspondence between file descriptors, which the applications read or write, and UDP port numbers or TCP port numbers, which is for the sort of endpoints of conversations that these file descriptors refer to. So the socket layer has these tables of file descriptors and port numbers, and it also typically has a queue of packets that have arrived and are waiting to to be read by each socket or file descriptor. And the software we provide you has a very primitive sockets layer. Underneath that are going to be the UDP and TCP protocol layers. UDP has almost nothing going on. It basically looks at incoming packets, extracts the destination port number, and hands the packet off to the socket layer so that payload isn't queued on the correct file descriptor's incoming queue. TCP actually is much more complex. It keeps state for each TCP connection, and it remembers all kinds of sequence numbers and packets that haven't been acknowledged and need to be retransmitted. So there's a huge amount of state in what's called a protocol control block in TCP, and virtually no state in the UDP layer. These are often called transport layers, UDP and TCP. And we provide you with a simple UDP layer, but not a TCP layer. Underneath TCP and IP is a IP layer, which is often fairly simple and kind of in parallel with the IP layer. I'm not sure whether I should draw it on the same level or underneath it is the ARP layer. Under them both, we can think of as an Ethernet layer, but it's really, there's not typically a separate Ethernet layer. Typically, there's one or more NIC drivers at the lowest layer, and these talk to the actual NIC, network interface hardware, which itself has a connection off to the local area network or whatever kind of network you're attached to. And sort of at this level, what happens is a packet arrives off the network, the NIC, pulls it off the network, hands it off to the driver, and the driver essentially pushes the packet up the networking stack. And at each layer in the stack, that layer's header, the IP layer will look at the IP header, verify the header, strip it off, hand it to UDP. UDP will figure out what file descriptor to queue the data on and add it to that queue. So packets come in and are parsed, and headers are stripped on the way up. And when an application sends a packet, the reverse thing happens. As the packet moves down through the layers, more and more headers are added on until you get to the bottom layer, and then the packet's handed to the NIC for transmission. And so, of course, the software, the way people think about and design network software in the kernel is typically driven by the nesting of the protocols inside the packets. Any questions about this structure? There's actually one important thing that I kind of left out here that sits on the side. There's buffers. There's packet buffers all through this. So when a packet arrives, it's copied into a packet buffer, and the packet buffers are sort of sent up and down the stack. And there's often quite a few packet buffers. There's often queues between these layers. There's certainly a queue here of packets waiting to be processed by applications. And this will be a linked list of buffers. And so there's a buffer allocator that's this buffer scheme and a buffer allocator that's used throughout the stack. And in the software, we give you the buffer scheme is called mbuffs. So there's kind of a mbuff scheme that's not a layer, but is used all throughout these layers. Okay, this is the layering diagram of sort of typical network stack. For this paper, it's actually important to understand how the control flow works, which is maybe a little bit different from what's in that diagram. One thing to know about network stacks is that there's typically multiple independent actors that process packets and take input, think about those packets, and produce output. And for various reasons, these different actors are decoupled so they can run concurrently and have packet queues connecting them. And so that's extremely important from the point of view of this paper. So within the kernel, so again, we have a network interface card, and then we have the kernel. A classic arrangement here is for the NIC to somehow get packets, for the NIC when it receives a packet to generate an interrupt. And there's this interrupt routine that gets triggered whenever there's an interrupt. And the job of the interrupt routine is to get the packet from the NIC. And because we don't want to dedicate CPU time to completing the processing of the packet now, the interrupt routine typically just appends the packet to a queue of packets for later processing and then returns. So it sort of does the minimum work required to get the packet from the NIC and put it in a queue. And the reason why we want to transfer, or in the sort of traditional network stack, we want to quickly move the packet out of the NIC and into this software queue is that NICs typically have a very limited amount of memory for queuing packets, whereas in the main memory, the RAM of the computer, we might have gigabytes of memory. We have so far more space here. So the NIC, if there's a burst of packets, the NIC may actually run out of space to queue them. So we copy them this queue here to avoid the NIC running out of space. And then separately, perhaps in a separate thread, there's what I'll call the IP processing thread. And sometimes it's not a thread, sometimes it's a sort of different kind of entity, but its basic job is to read packets off these incoming queues. And there may be multiple NICs, appending packets to these queues. So our IP thread runs, it looks at packets that are been queued here and decides what to do with them. One possibility is to send them up through UDP into the sockets layer to be queued, waiting for some application. And typically this will just be a function calls here within the context of this thread. Another possibility, and this is the possibility the paper cares most about, is that this host is actually a router, and its packets are coming in one NIC and routed out one or more other NICs, because it's very common to build routers out of ordinary operating systems like Linux. Like if you buy a Wi-Fi box now or a cable modem router or something, it's extremely likely to be running Linux internally and to use the standard Linux stack, which has a complete router implementation. It's highly likely to be using the standard Linux stack in order to do its routing. So if the IP thread looks at the destination IP address and decides, oh, I should send this out, I should forward this packet out, out another network interface, it'll add the packet to a queue of outgoing packets for this outgoing interface. And there's almost certainly, so this is a receive interrupt, or RX for receive. There's usually some sort of transmit interrupt scheme for the outgoing NIC. And the NIC will interrupt whenever it's finished sending one packet and is ready to be handed more packets. So these outgoing interrupts may also be important. And the point here is that there's a bunch of concurrent entities that are sort of separately scheduled in various different ways. These interrupts are triggered by the NICs asking for interrupts when packets arrive or when packets have been sent. This thread may be a kernel thread like we have in XV6, and on a uniprocessor, as was the case with today's paper, this thread can't run at the same time as an interrupt. The interrupts have absolute priority. On a multi-core machine, there may be more parallelism. And then if it's important that applications to be able to read the packets, the applications are yet another sort of independently scheduled entities that we'd like to get their chance at executing on the CPU. So these are all the players in the scheduling game, essentially. One thing that comes up a lot is buffering. So there's 3 queues here. By buffering, I mean these structures in which one independent entity appends input packets and some other entity pulls packets off the front of the queue. These queues are pervasive in networking systems. One reason for them is to allow temporary cope with temporary bursts. You know, this IP thread maybe can only process packets at however many per second, but the NIC may be able to deliver packets much more quickly. And so there may be a little sort of temporary burst of packets. We'd like to have somewhere to put them, waiting for the IP thread to get around to processing them. And so that's one use of queues. On the output side, another use of queues is we'd like to, especially if packets are bursty, we'd like to be able to stack up a bunch of packets here ready for the NIC to send, to keep the NIC, to output NIC busy. Because depending on the speeds of things, it may be quite important to be able to utilize 100% of the network here. And the other reason for, or maybe the same reason stated differently for having queues, is to be able to structure software into independent parts that are scheduled separately. Like, we wouldn't necessarily want to have our IP thread or the application know about the other things that have to go on, like interrupt processing. So the IP thread is sort of, in traditional networking system, you know, doesn't necessarily know when interrupts happen or when applications run, although we'll see in this paper that there may be advantages to having a little bit of knowledge there. Questions about this sort of scheduling control diagram?
I have a quick question. So can the same NIC not be used for both transmitting and receiving?
It can.
Like, why do you, oh, it can, okay.
So my laptop really only has one interface, and it connected to Wi-Fi. When it receives a packet, so on my laptop, this NIC is actually a Wi-Fi radio interface. Packets arrive and go out on the same NIC. The two NIC situation is certainly used for routers. So your home Wi-Fi, I don't know, maybe I have Wi-Fi and cable, and there's a router box that has two NICs. One is its connection to my cable modem, which leads to the rest of the internet, and the other one is the Wi-Fi interface. So the little box that the cable company sent me is a router with two network interfaces.
I see, makes sense.
And there's actually a lot of servers have multiple interfaces also, especially ones that are web servers that, you know, you want to talk to the outside world at one interface and to your private sensitive database machine or something on a totally separate network with another network interface.
I see. So
this arrangement's pretty common.
The criteria for having multiple NICs is just wanting to talk to different networks then?
Yeah.
Okay.
Yeah, if you want to talk to different networks, then you would have multiple NICs, yes.
Got it.
All right, I want to, as an aside, talk a little bit more about NICs, what NICs do with packets when they arrive. And this is of a special relevance to the lab. You know, what a NIC looks like internally, you know, it's got a cable leading or a radio leading to from the outside world. You know, and it looks at electrons as they come in and sort of turns them into packets. And then there's the host, and the host has some sort of driver software in it. And one way or another, you know, we need to get a packet that's decoded in the NIC into memory where the IP software in the host can parse that packet. And so there's a lot of different schemes been designed over the years. The paper scheme is that the NIC has a lot of internal memory, and as packets arrive, the only immediate thing that happens is the NIC lays down the packets in its own buffer memory, and that's it, and interrupts the host. And so the NIC has an internal queue of packets and a bunch of memory, and then in the in the host driver has a loop in it. The host driver will talk to the NIC and say, "Oh, you don't have any packets buffered?" And if it does, the host has a loop that'll just copy, you know, byte by byte or word by word, copy this packet into the memory of the host and append it to a queue inside the host. So that's how the paper's NIC works. The driver sort of is responsible for doing the copy from NIC memory to host memory. That made a lot of sense 30 years ago. Today, though, it turns out that loops in the CPU that copy, that talk to external hardware or hardware sitting on buses are very, very slow. This is sort of there's a, in the grand scheme of microprocessor design, this distance here between the CPU and an external device, even if it's on the same computer, this is a very long distance. And each conversation today takes a long time for each back and forth chit chat. And so you don't want to have a lot of byte by byte interaction. So people don't design high-speed interfaces like this anymore. And so a much more modern arrangement looks like this. And so now I'm going to talk about an arrangement which shows up in the E1000 NIC, which you'll use in the lab, or simulation of which. So the way the E1000 NIC works, so it has its wire and it's looking at the electrons, but as the packets arrive, the NIC writes them. The NIC doesn't really have significant internal buffering, although it has a little bit. It actually copies the packets directly into host memory, where they'll be sitting there in host memory waiting for the driver to pick them up, sort of already copied. But that means the NIC has to know where in memory it should put each packet. The way that E1000 NIC works is that the host software formats up what's called rings, DMA rings of packet pointers. So a DMA ring is just an array of pointers to packet buffers. So the host driver, when it's initializing the card, will allocate however many, say 16, 1500 byte packet buffers. Will create an array of 15 pointers or 16 pointers and make these pointers point to there. And then it'll tell the NIC in configuration time, look, here's the ring. So this is called a DMA ring because after you've gone off the end, you start back at the beginning. The driver software will tell the NIC, look, here's a pointer, the address in my RAM of the ring, the DMA ring that you're supposed to use to deposit incoming packets. So when a packet arrives, the NIC will actually remember which ring entry is the next one. Well, it has a little pointer here that allows it to remember the next entry that it should DMA a packet into. When a packet arrives, the NIC will fetch the pointer fetch this buffer pointer out of the host RAM, copy the packet bytes into this buffer, and then advance its internal index here to point to the next ring slot, which it'll use for the next packet. And there's a similar, so this will be the RX ring for receive. There's a similar ring that the driver sets up in which the driver puts packets that it wants the NIC to send. So the NIC also has a pointer to the TX ring. And so you'll learn your job in the lab is basically to write the driver software that handle these rings. Any questions about this arrangement?
Yeah, how does the E1000 compare with production level NICs that may be used in high performance environments?
Well, when the E1000 came out, it was the absolute best NIC available. And it was the NIC that was used in serious production environments. But that was however many years ago. Modern NICs are quite a bit cleverer. What hasn't changed that much is this DMA ring structure. You still find that NICs, they use DMA to deliver packets, and the way they find the place to deliver the packet is by these rings of buffer pointers. There's a couple of things that modern NICs are more clever about. One is that modern NICs, you can set them up with many, many queues. The E1000, I think, just has a single receive queue. But you can tell a modern NIC, look, I want you to split my packets up into 32 different incoming queues, and here's how to decide for each packet. Look at this field and use that to choose which ring to DMA the packet into. And there's a whole bunch of clever ways that people use that capability. Like if you have multiple virtual machines, you're Amazon and you're running many guest virtual machines, you may use that capability to sort of direct each packet to the queue corresponding to the virtual machine that packet should be read by. And another way in which modern NICs are more clever is that they'll do some of the TCP processing on the NIC, like maybe typically checksum calculation is the most thing. Anyway, yeah, so modern NICs are like the E1000, but more.
Okay, thanks.
Other questions?
Sorry, go ahead.
Oh yeah, I just wanted to ask, so in our scheme in the lab, there is no queue between the IP layer and the driver, right?
Yeah, the lab network stack is stripped down to the absolute minimum. It's far simpler in structure than a real network stack.
But this is worse in terms of performance?
Oh, I don't know. Who would know? I never run it in real life. I'm sure. I mean, we paid zero attention to performance when writing the lab network stack. So it would be surprising if it had good performance. But
I see.
Mostly it's not a question of performance, but there's limitations. It doesn't do 95% of what you need a network stack to do, like handle multiple NICs or have TCP.
Right. Okay, I see. Thank you.
Sorry. So were there any like hardware changes to like the overall system that were needed to enable like NICs that have direct memory access? Like in the previous picture, was everything mediated through the CPU, or could NICs also like reach the memory directly?
In the picture I showed before, no, the NIC doesn't reach into memory at all.
Okay.
I actually don't know. I mean, maybe the most important question is how virtual memory, whether and how virtual memory translation works when the NIC wants to use an address that refers to host memory. And I don't actually know how that works. I don't know how that works. I suspect there's translation. You know, the NIC is really sitting on a bus that's connected with, through some fairly intelligent silicon to the DRAM system. And I believe in modern machines, you can set up translation tables so that the NIC could use virtual addresses or addresses that are translated by this hardware that sits between it and RAM. And that could be very valuable for some situations. The other thing, another thing that I'm aware of is that if the NIC is going to write some memory or read some memory, and the memory is cached on the CPU, you want the NIC to read. If the software just wrote a packet buffer, but the CPU hasn't, the CPU is merely cached the write, because after all, most memory is write back. That means that the real latest version of that memory is sitting in the CPU cache, not in RAM. And in that case, we'd like the NIC to be reading the CPU cache, not the RAM, if it does DMA. And certainly on Intel machines, and probably on others, there's some fairly elaborate machinery so that if the NIC reads some memory, but the latest copy of that memory is in the CPU cache, it's the CPU cache that will produce the data and not RAM. And that's that's actually a facility that some clever software uses to get high performance. That is to have the effect of having the NIC, this happens for writes also, that the NIC will essentially directly write cache lines in the cache where the CPU can get at the data very quickly. Cool. Yeah, so this picture is simple, but the real life, it's pretty involved. Other questions about anything? Okay. I'd like to switch gears now to today's paper. And I'm just gonna because we've already talked about a lot of the background of this paper, I'm just gonna go directly to the first graph in the paper. And essentially to drive the discussion off of the paper's graphs. And so what we're looking at here is the performance graph for a router. On the x-axis, there is a router with 2 NICs. Its job is to packets come in 1 NIC, and it's supposed to just send them out the other NIC. The x-axis is the arrival rate, which packets arrive at the input NIC. And the y-axis is the output rate at which packets are observed to leave the output NIC. The line we care about is the filled circles, which goes up and then down. So even without knowing anything about what's going on here, we can look at this graph and we can ask ourselves, gosh, why does it go up? Why does it go down? You know, what's special about this point that's an inflection? You know, what is it that governs how fast it goes up or how fast it goes down, right? So even with zero knowledge, we kind of have a good clue about what questions to ask. So why does it go up? Why do these dots go up? It's not a very deep question. They go up. Sorry, go ahead.
Oh, because when they're like, until it gets like saturated, you can process more input packages and produce more output packages.
Absolutely. Like until something starts to go wrong, for every packet that comes in, the router just forwards it out. So, you know, until things go wrong, if packets arrive at 2,000 packets per second, well, it just copies every input packet to the output. And that means that the output rate is just equal to the input rate. So this is just y equals x, you know, because every input packet gets sent out. So it's y equals x for a while. And so why does it stop going up?
Isn't this the one thing they mentioned in the paper about there being interrupts that can't be processed at the necessary rate?
That's the answer to the question, why does it go down? My question is, why does it stop going up? Like, what is it that, could this line in a well-designed system, supposing that they hadn't messed up the design, right? You and I would design a system that didn't have problems, right? Would in our system, would the line just keep going up?
I guess not, because at some point the rate at which packets come will, if you can process packets fast enough, then at some point the bottleneck will be the rate at which packets arrive. That's
right. The system we're talking about has sort of limits. It's not, the CPU is not infinitely fast. The CPU executes however many instructions per second and no more. So each of these packets has to be processed. The IP software has to look at the header and check the checksum and look up the destination addresses in the table, whatever. It takes hundreds or thousands of CPU cycles per packet. And so we can never expect these lines to go up indefinitely. They must stop somewhere, right? And we can sort of tell we can make some guesses on this system. It goes up to 5,000 and no more. And what that basically suggests to us is that it takes about 200 microseconds on this computer to process each packet, right? That's what this point, the fact that the inflection point is here suggests that the total cost of processing a packet is around 200 microseconds of CPU time. You know, that's a guess, but it's likely to be close to correct. And so there's just no way we could get, you know, maybe we could make the software a little more efficient. Maybe we could reduce that to 150 microseconds per packet or something. And so maybe we could move the inflection point up a bit, but we're certainly faced with some point at which, well, that's just how many packets the system can process. Now, that's not necessarily what's going on here. Right? It happens to be what's going on here, but it's not written in stone. In fact, there's other bottlenecks that could be the limit other than CPU time, which are worth considering. The most obvious is the speed of the network. The network they were using ran at only 10 megabits per second. That's just how fast the low-level networking hardware sent bits. And so it can never transmit more than 10 million bits per second. And so that may also constitute a limit. And so we're thinking about whether maybe that's actually what's determining this 5,000. The paper doesn't quite say enough to know whether it's CPU or the NIC that's the limiting factor here. But the fact is, with their 10 megabit network, if you send small packets, the 10 megabits translates into something like 10 or 15,000 packets per second. So that's the limit that the networking cable puts on the input rate. And so this is well under the 10 or 15,000 packets per second that the network is capable of. So almost certainly the limit has to do with CPU or memory or something, and not the network itself. Okay. What we'd love to see in a well-designed router is that that it can actually have, if it takes 200 microseconds to forward a packet, to process a packet, what we'd like to see is that the router can actually forward 5,000 packets per second, no matter what, even if the load is high. So what we would like to have seen is this line here, where the output rate matches the input rate until you get up to the capacity of the system, 5,000 packets per second, and then it just continues to forward 5,000 packets per second and presumably discards the rest. So this is what we'd like to design, but what actually happened is much worse than that. As you increase the rate beyond 5,000, the number of packets that it manages to forward goes down towards 0. So why does this line go down? I think somebody mentioned this before. Well, the reason that the authors figured out is that as you increase the input rate, each of these input packets generates an interrupt. And the interrupts take time. Actually, on their system, the interrupts are quite expensive because they involved copying a packet off of the network interface card and into main memory, which took a long time because the CPU was doing it. So we know if packets are arriving at 10,000 per second, we certainly can't forward 10,000. And that means the best we can hope for is to forward 5,000 and simply discard the other 5,000. But in fact, the extra 5,000 packets each generate a very expensive interrupt. So for each additional packet over 5,000 per second, we're generating more and more expensive interrupts, which have priority. Like interrupts, boy, whatever you're doing, it stops and the machine takes the interrupt. Because the machine is essentially giving priority to these interrupts, that means every additional packet per second is taking CPU time away from the forwarding code until finally 100% of the CPU time is used up in the input interrupt routine, and no CPU time is used in the thread that forwards packets. Is everyone happy with this explanation? And this going down is called interrupt live lock. The fact that this line goes down instead of staring flags is what people mean by interrupt live lock. And it's actually a phenomenon that occurs in many systems. I mean, the sort of thing that's driving it is that there's two separate tasks, like the input interrupt task and the forwarding task. And because of a scheduling problem, essentially priority is given to the input task, which can starve the packet processing task. And in pretty much any system that has multiple independent tasks or sort of sequence of independent tasks that need to be done to each input, and in which the input rate can't necessarily be controlled, many systems like that will exhibit live lock if you push them too hard. And you can get live lock due to many resources, not just CPU, but it could be that the NIC, a NIC that DMAs uses up RAM cycles to do the DMAs. And if the NIC is using the RAM, the CPU can't use the RAM. So another way to get live lock, even if you have lots of CPU time, in some other design, you might get live lock because the NIC is using up RAM resources, RAM performance resources. So the CPU is less able to use the RAM. Anyway, this line going down is what they mean by live lock. You may ask what happens to the excess packets. And if you recall, the structure of their software was that they have a NIC that basically feeds the receive interrupt. The received interrupt software copies each packet into a queue. And then there's some sort of network thread that pulls packets off the queue. The exact place where packets are lost are right here. What's going to happen is that the interrupt routine, once we get down here with serious live lock, the interrupt routine is going to fill this queue. There's going to be some maximum queue length here, at least all of RAM, but probably much less. And the interrupt routine is going to pull a packet off the NIC and see that this queue is already as long as it's allowed to be, and the interrupt routine will discard the packet. But then, of course, immediately after that, there'll be another interrupt. And the interrupt routine will again discard the next packet because the network thread is always interrupted and never allowed to run. Questions about this diagram? This is the most important diagram in the paper. All right, well, we've basically run out of time, so I'll try to compress the answer to this problem into a minute. The authors propose a solution. The most immediate good news about the solution is that this is the performance of their solution. That is, the input rate goes up to 5,000, and then it's flat at 5,000, regardless of input rate. So this is sort of a perfect non-live lock performance line. Of course, it's going to be flat because we can only process 5,000 packets per second due to the speed of the CPU. And the way they get this, they still have this network thread. And they still have an interrupt routine. And so the very first time the NIC interrupts, it'll run the interrupt routine, but the interrupt routine does not copy packets off the NIC. It wakes up the network thread and then leaves interrupts on the NIC disabled, so we'll get no more interrupts. Wake up the networking thread, and then the interrupt routine will return. So now interrupts in this NIC are turned off. The network thread basically has a loop that it'll check the NIC, pull a few packets from the NIC. 5, I think, is what they ended up using, and then process those packets. And then if there were none, if this, it'll check so it's this networking thread now that reads packets off the NIC, not the interrupt routine. If there were no packets waiting, it enables interrupts. And then goes to sleep. Because it's enabled interrupts, the next time a packet arrives, the interrupt routine will wake up this thread, and it'll come out of sleep and go back to the top of the loop. And so this is the structure of their solution. And one way to view this is that they turn an interrupt scheme into a polling scheme. That is, under high load, they just sit in this loop, and they read a packet, process it, read a packet, process it, with interrupts turned off. So since those interrupts are turned off, they never get this effect where the interrupts steal time from the main thread. Whereas under low load, they enable interrupts, and maybe a while until packets arrive, but they'll be woken up by the interrupt routine immediately if a packet does arrive. And that's all I have to say. Any questions?
I have a question. Is that loop looking at all of the devices or only the one that generated the interrupt?
If there's multiple NICs, so that's a good question. If there's multiple NICs, the loop, I don't actually know how the loop worked. A very reasonable design is for this network thread to keep track of, for every NIC, whether it's in interrupting mode or polling mode. And then it will only Actually, because the interrupt routines no longer read packets from the NIC, that means the loop probably checks every interface at this point. Probably checks every NIC at this point and pulls up for every NIC. If it has a few if that NIC has packets waiting, the loop will pull a few out of the NIC and process them. And then if none of the NICs had anything, if it checked all the NICs and none of them had any packets waiting, the loop will enable interrupts on all the NICs and sleep. And any NIC that interrupts will wake it up. That's my guess.
Okay, yeah, sounds reasonable.
I had a quick question then. So how do so while the loop is running, how do packets actually get into the queues to be pulled? I felt like there would only be one at a time.
Initially, the packets are queued inside the NIC in its own private memory. Then this loop, when it goes back to the top of the loop, it'll look at each NIC and actually talk to the NIC hardware and ask it, do you have any input packets waiting in your memory? And if it does, then this loop will allocate a packet buffer in RAM and copy the bytes of the packet out of the NIC into the packet buffer and then process that packet buffer.
So it can copy more than one packet?
Yeah, I think they would
okay.
do it in groups of 5 in order to, even if there's 100 packets waiting here, it would just process the next 5 in order to be fair among input NICs and to avoid starving the output.
But this requires increasing the memory capacity of the NIC, right? Possibly?
Well, I don't know. I don't know how much. The NIC might have had a reasonable amount of. The thing is, this interrupt, this live lock phenomenon, like below this point, we're probably interrupting. And if a packet arrives, the network thread will almost immediately be woken up and pull the packet out.
Yeah.
If we're over here in this regime where too many packets are arriving, and this loop is polling instead of interrupting,
mm-hmm.
packets are going to be lost. We just know that because the difference, this difference between the input rate and the output rate, this is all dropped packets.
Yeah, yeah.
And I don't think adding, because these packets are going to be dropped anyway, adding buffering to the NIC probably doesn't help very much. I don't.
Oh, okay.
I think it's a NIC. It's not clear the NIC needs more than a small amount of buffering.
Yeah, that makes sense. Yeah, you only need as much as it would need to to get saturated.
So, I think in their design, they would pull 5 packets if their quota was 5 packets. And so the NIC certainly needs 5 packets of buffering for that to make sense. But it probably, anyway, it's not clear that more than that would be very beneficial. Really, the purpose of buffering is to absorb transient bursts. So hold the packets long enough that the software can get along to reading them. But we're not talking about transient anything in this situation. We're talking about persistent overload. So that means there's not really much function for a lot of buffering.
Yeah, makes sense. Thank
you. I think my question is related to that. So if the difference between interrupts on and interrupts off here is that it's going to be the same, but like it's still going to be putting things on the queue if it's able to, but it will just not issue an interrupt. But if there's no place on the queue, then it will just drop.
The interrupt routine in this new scheme never looks at packets.
Oh, yes. I mean, like you said that you turn off the interrupts for the NIC, right?
Yeah, so what happens in the interrupt handler is it disables interrupts on this NIC and then wakes up the network thread. And that's all it does. And it returns.
Right. I guess my question is, when the interrupts are disabled, can the NIC still put packets on its own buffer?
Yes, the NIC is self-contained. So it has internal buffering, whether or not, regardless of whether interrupts are enabled or disabled, all that happens when a packet arrives is that the NIC appends the packet to its queue of packets in its own internal memory. That's all that ever happens when a packet arrives. So it never, the NIC, in this paper's NIC, I mean, different NIC designs are very different, but for this paper, their NIC never did DMA. It never reached out and touched host memory ever.
Okay.
It just kept an internal queue in its own memory, and the host could read packets out if it wanted to.
Okay, I see. And if there's no memory, then
drop.
Okay.
So in this design, if packets are these excess packets, the place they're dropped is inside the NIC. What'll happen is a packet will, you know, if we're in an overload situation, then the NIC's queue will be full always, or almost always. And so when a packet arrives, the NIC's queue will typically be full, and it'll drop, the NIC will drop the packet without wasting any CPU time on the main machine.
Okay, yeah. Okay, yeah.
The fact that it can drop without burning up CPU time here is one way of explaining how they avoid live lock.
Right. Okay, thank you so much.
I had a quick question. Will there ever be a scenario in which the CPU loop will pull a few packets, but the internal software queues are all full?
Oh, sure. Yeah, there's some other bottleneck. So, for example, suppose these incoming packets, some of them need to be delivered to some application on a socket. If that application isn't reading packets fast enough, then the socket buffer leading to, you know, that application should be reading will get full, and then packets may be dropped in the networking thread. And that can also lead to live lock. Because we have this same, the reason live lock comes up is that we expended resources processing a packet that was later dropped. So it was wasted effort. If the application's not reading, one way we can get live lock is as the load goes up, maybe we end up spending 100% of our time in the networking thread, leaving 0% of the time for whatever application is supposed to be reading the packets. And then we'll again get live lock. But it won't be interrupt live lock. It'll be network processing live lock or something. The paper actually had a story for that. Somewhere in section 6, they talk about the network. If packets are being delivered to a local application, the network thread would look at the socket queue for that application, and if it was getting long, it would turn off interrupts and stop pulling packets off the network interface until the queue got shorter. And so that means the network thread would stop running and give the application a chance to run and process the packets. So you can get live lock-like situations at any stage if you're not careful in that kind of multi-stage processing scheme.
Okay, that makes sense. Thank you.
Yeah.
Thank you.
Thank you.
You're welcome.